Hi guys, welcome to Automation and Control System Academy. Today exercise we are going to discuss about control system, and this particular control system is called Star Delta Motor Control. This is my Star Delta Motor Control. Now this portion is my control system control circuit, and this one is my power circuit. We're going to discuss about the operation sequence and the safety that is associated to this particular device. Let's discuss about the safety first. Then subsequent exercise, we now learn how to design the control circuit as well as the power circuit. Now the safety is this. Induction motor, due to the prime operation of this particular device, there is a voltage drop limit set aside that motor must work within. So the acceptable voltage drop limit is going to be 5% of the nominal voltage. That means before you subject this motor to operation, make sure that the supply voltage does not drop more than 5% of the supply range. If you are using 400 volts as a case study, 5% of 400 volts should be 380 volts. So voltage drop shouldn't go below 5% so that it does not prevent the motor not to perform optimally or drop the efficiency of the motor operation. So that is why the 5% are set aside for the motor to work safely. So take note of that. Another safety implication we need to look at is phase failure. There's a device called phase failure. So while designing this, you should also make sure you incorporate the system with phase failure device so that sorry, when each of the phase of the supply, any of the supply phase is lost in terms of phase failure, one of the phase is out, the system should shut down. Or if the phase is failed already before energizing the system should not get energized until the three phases are complete. Now, another safety implication you need to look at again is the phase sequence. Now, in the order of line 1, line 2, line 3, for you to subject this motor to run within this termination order, it must be in this order. You shouldn't swap any of this phase arrangement. Like line 1 shouldn't be come to line 2 shouldn't come to line 3. So the order of line 1, line 2, and 3 should be this way. If you swap any of the two phases, the rotation of this particular motor will be changed. If it was designed for clockwise operation, it will now go counterclockwise. If it is also counterclockwise, it will also go to clockwise whenever you swap any of these three phases. So you should also make sure that during your design, this particular device is incorporated, right? Okay, so these are the safety measures you have to put in place while working on this particular design. Then the next one again is the operation sequence. Operation sequence goes this way. Because this is a star delta motor design, you are expected to design the control in such that the star contactor get energized first. I repeat again, the star contactor should be energized first, where in practical, the mains contactor and the K1 being the star contactor get energized simultaneously in practical. But in your design safety coordination, you should also interlock, you should also prevent mains contactor not to get energized should anything happens to star contactor. If star contactor is faulty, thereby not getting energized, this other contactor and these two shouldn't get energized as well. But in practice, these two get energized first simultaneously, K2 and K1. Thereafter, after a few seconds, depending on your setting, 3 seconds to 4 seconds, star contactor should get de-energized and delta contactor should take over. Both of them should swap operation. While this one remain in operation throughout the operation time. I repeat again, the safety aspect of this is that Star contactor, your control system should be designed in such that star contactor be made the master of the entire system. Star contactor should get energized simultaneously with this. Then in a situation where star contactor is faulty and couldn't get energized, none of these two contactors should be allowed to get energized, right? Okay, if that is taken, that means the coordination of this particular operation should be dependent on the design of the control circuit, right? The essence of you making the star contactor to be the master of these two is that this particular induction motor demand voltage flow and current flow through two paths. Take a look at this. This is the supply. We have a divert voltage flow from here. We also have another divert from here. So current flow two part. This is one part and this is one part. So when you want to run the motor on low speed, this one shouldn't close. This one only and this one should close. So the voltage pass through one part only. Then when you want to subject the motor to high speed, that is want to work on maximum efficiency, this one should get energized, this one disengaged. So voltage now pass through two parts, one here and one here. So once the voltage passes through two parts to this motor, motor go now to full operation. That is the high speed. Now, before this one changes over, before the delta contactor changes over for the motor to be subjected to high efficiency operation, this one will first of all close, thereby forming a start point to the induction motor winding. When here closes, it's now forming a start point to the motor, thereby creating a single phase operation and the voltage flow only one part. Then when this one get de-energized and this one energizes, then 400 volts coming from here will be diverted through this part and through this part, right? So control system should design in such a way that this particular sequence be made available for the motor. Otherwise, if this sequence is not being followed and you end up making your mains contactor to be the prime device or to be the master of these two, the risk implication is that when this one closes, and in terms of fault, none of this one closes, the voltage can go to the motor. And motor remain, either the motor will hum or the winding will be damaged or a risk from the operator because it is assumed that motor is not energized. In that case, there is no power to the motor. Meanwhile, this one is energized already, so the motor is energized partially. So when you are working on the motor with idea that the motor is not energized, should be careful because this one has closed. The winding has power, and these two they are not closed. And the motor is not in operation, but there is a voltage and current to the motor. So that is the risk implication of making this particular contactor the master to these two. So this one should be made master so that if this one refuses to engage, these two shouldn't also come in. So in that case, starting from here to here is cut off. There's power here and no power to the motor. So the safest design is to make your star contactor the master to these two. So that if this one fail to energize, none of these two can also be energized. So that is the safety aspect of this particular design, right? So our next exercise, we're going to talk about the control, how you design the control, how the operation also should go. But for the meantime, I think we can also simulate. Let's see if we can simulate, put it on like this. Power comes in to this area. I want to energize the system. I push this button. Once I push this button, it's not any right. Okay, this one is malfunction somehow. When I push this button, this one comes up. It now changes after 3 seconds. Okay, let me see if I can increase the time interval to enable you see the function. Let me make it 5 seconds. All right. Okay, now let me put on the equipment. I put on the system this way. This one come up and this one close. these two close simultaneously.